Welcome, everyone. Thanks for joining us. I'm Ryan Evans with the Center for Agricultural Profitability at the University of Nebraska-Lincoln. And as you may know, this is part of our regular webinar series, which is usually held every Thursday at this time, noon Central. And do check out our website. I'll be dropping some links in the chat throughout the webinar today where you can find that. We have information on all of our upcoming webinars, registrations, as well as recordings from past webinars that go back about 4 years now. That's cap.unl.edu. As you have questions today, we would love to hear from you through the Q&A box in your Zoom window. So please enter those in as they come up, and we reserve some time at the end of the presentation to answer those. Today, we'll be looking at farm energy management, and farm electricity costs, of course, are significant on a farmer ranch, and saving on electricity many times goes beyond energy efficiency or reduced energy use. Today, we'll explore how farms and ranches are charged for electricity and ways to identify and possibly slash those costs. To present, we are glad to be joined again by F. John Hay, an extension educator for energy in UNL's Department of Biological Systems Engineering. John's work focuses on energy systems and energy issues, including renewable energy, biofuels, and specifically economic return for home, farm, and business solar electric systems. And again, today he's going to be covering electricity and saving on those costs. So hi, John. Thanks for joining us again.
Glad to be here.
And we also have on with us Rick Stowell. Rick works with John and on a lot of things. He's a professor and animal environmental engineer in UNL's Department of Animal Science. Hi, Rick. Thanks for joining us.
Hello, I'm glad to be here.
So Rick will jump on at the end to help answer any questions that might come in during the presentation. And again, we encourage you to put those in the Q&A box so we can address those at the end. But for now, I will turn it over to John.
Thank you, Ryan. I'm glad to be here. I brought this topic up when I had lunch with Rick a while ago and said, things are changing so much in the world of electrical rate schedules and things. It'd be a really timely topic to get this in front of, farmers and ranchers and even just everyday Nebraskans, because this is changing across all types of rate schedules. So we're focused on electrical energy today, and we're going to talk primarily about the major components in our electric bill. And I'm going to show you some times where those are pretty easy to understand and sometimes where they're much more complex to understand. We're going to talk about energy, demand, and power factor. I do have some example rate schedules that I went around the state and found some different rate schedules and then just made a kind of a mock version of that rate schedule for us to look at. So I have some kind of examples that'll help us understand what we're talking about. Let me see if I can get this all pulled up. But, I titled this The Rules of the Game, but I'm really thinking about how are we trying to approach this? We start with this rate schedule, how we are charged for electricity. And that's going to dictate how we're going to, over here in the green, how we're going to actually get the savings in the end. But it's combining how that rate is charging us for energy with how we're using it. And, I'm not telling you we have to turn around and use our electricity completely differently because we're running our operations, we're living our lives, but it's a matter of trying to understand and match those two so that when we do make management practice changes, we can make sure those have the best impact possible. So how are we charged for electricity? If we were to look at our electric bill, sometimes these things that I'm going to list show up. Sometimes they don't show up on our electric bill. Sometimes they show up on our rate schedule. And sometimes they don't even show up there, but they're there, trust me. So we're always going to have some type of fixed charge, some type of charge that is like you use no electricity at all. They're having a charge for you to be connected. It's sometimes called a customer charge. It's sometimes called, there's other words for it, but you'll see that, and it ranges between $5 and maybe $50 in the state of Nebraska for kind of that small rural or rural residential rate, which many farms are on that rate structure. We're almost always charged per unit energy that we consume. That makes sense to us. I bought a gallon of gas, I pay for the gallon of gas. I charge for the energy. But electricity is a little different in the sense that the rate at which I use it makes a difference, because the utility has to size its infrastructure to deliver at those peak rate times and deliver us at that peak. So demand is increasingly important, and we're increasingly charging for demand at more and more rate structures. I'll talk about that in a minute. And also power factor, which I'm going to detail later, but power factor tends to be an adjustment in demand when it's charged for. So transmission and distribution is delivery. This is like buying something online that costs $1 with a $2 delivery charge. And as long as $3 is what we're happy with, we order it and we pay the delivery. Well, electricity has to be delivered. There are transmission and distribution charges. Sometimes they show up on our bill, sometimes they don't. But they're there. They're trying to make whole for that. There's also kind of a variety of other small charges that show up, taxes and riders and cost recovery charges, and I just kind of have those all grouped together as other types of charges. Really, the utilities are out there trying to make this system function. And so the customer charge might go to kind of infrastructure and overhead, making sure that they're whole on that. The energy, they're trying to pay for the actual generation of the electricity that they purchase or make. Then you have transmission and delivery charges, that the distribution and transmission charges that kind of pay for, again, the infrastructure to get that to us. The high voltage all the way down to the low voltage. This is just a bill I pulled off of OPPD's website. So not really picking on OPPD here, just using their example bill because it was one that was available and it gave me some of the things I wanted to show. But when you pick up your electric bill, you usually can find some basic information like, in this case, I'm just going to point out how much electricity was used during that billing period. And so that's the energy use. It also has the customer charge there of $30. It has the energy per the kilowatt hours and then the total energy charge. And then it kind of has these other additional charges. So what we're not seeing is any of the transmission or distribution. We're not seeing any demand in that. And really, we don't even know how much per kilowatt hour we're charged for that electricity. We don't know what we were charged for. Now, we could divide this kilowatt hour usage by the energy and get some estimate. But a better way to do this, and this is where you as a customer of the utility, I'm telling you, don't rely on your electric bill to tell you how you're charged for electricity. That information exists in the rate schedule that you're going to have to call and ask for. So I'll get rid of that. You're going to have to call and ask for it or get online. Many of the utilities have that online, not all of them. Sometimes you have to call and ask. But this is the rate schedule for the bill that I just pulled up. Clearly, I have my monthly service charge, which is that customer charge. But now I'm seeing that I'm charged differently depending on the time of the year and how much energy I use during each billing period. And this is giving me the more details that I need to be able to understand how I'm charged for electricity. And this is a relatively simple rate schedule, but it's got more information. So if there's anything that you get out of today, I want you to get on the website for your utility, download the rate schedule you use, and look at it. That's going to be really important to making any plans for savings in the future. In that rate schedule that we just looked at, we didn't see a demand charge and we didn't see power factor or transmission or distribution, but they're recovering those with this customer fixed charge and with this energy charge. So that's their philosophy of billing, is to make the money in the customer charge and the energy charge that cover those other kind of components. And so those components are being essentially covered. Those costs are recovered, but through those other charges. So not all bills have all these, but that's where we're going to get into some of the trends that are happening in Nebraska today. And I actually was reading some rate schedules yesterday and saw some of these trends coming true in Nebraska today. And I've been seeing it for a number of years. One of those trends is a shift from charging per kilowatt hour to a base fee. So they may have had a base fee that was very low, like $5, and a per kilowatt hour charge of, let's just make up a number to make it round, 10 cents. Well, the next year they're going to charge $15 for the base fee and maybe not raise the 10 cents. So it may or may not have gone down the per kilowatt hour, but it didn't raise. And so they shifted some of their recovery to that customer charge. We're seeing that quite commonly across the state. We're driving those customer charges up towards $30 to $50. And we're seeing fewer and fewer of those very low customer charges. We're seeing increases or addition of demand charges. This is both at the commercial rate schedules that a lot of farms are on, but it is also, I'm seeing this at least a couple times recently on residential rate schedules, and that could be like a farm and rural residential rate schedule that had a demand charge. So important. Time of use rates, where they charge different amounts for per unit energy, depending what time of day it is. I have an example of that in a moment. And then finally, adjustments for power factor that are typically adjustments to the demand charges. We're seeing that really, it's power factor charges have been an important thing in very large rate schedules like industrial and large commercial for a long time. We're seeing that filtering down. I'm seeing that in a lot of irrigation rate schedules the last couple of years. So these power factor charges are continuing to be adopted by more and more utilities. What's the reason for these changes? Now, some of it's just kind of the natural movement in the system. I think that we need to make sure that we're recovering the right amount of money so that we can keep these systems economical or functioning. But the other is that there are new advanced meters. Many of you know that the meters that actually had the little dial that spins, aren't there anymore. They're digital. They're their own little computers. And these modern meters can do a lot of things. They can record the time of day when a kilowatt hour was used. They can record the peak use or the demand. They can record the power factor or the load's impact on power quality is a not greatly correct way to call power factor, but it gives us a good idea of what it is. It can measure in both directions in the case of having meter renewables. And so that meter and the fact that it can measure all those things and report all that data back to the utility allows the utility to now have a more detailed rate schedule and charge for the different pieces that they want to charge for that makes them whole. So if somebody's causing them low power factor, that person should be paying for the low power factor, not necessarily everybody. And so they're able to move that cost onto the correct place. Now, this is just a little overview of utilities in the United States just for fun, because we all know, or many of us know, that Nebraska is a public power state. But what does that mean? In what it really means is that all utilities by statute are publicly owned. And so they're either publicly owned or cooperative in this case. So there are some cooperatives here. Those are considered publicly owned. But you can see Nebraska is a little bit interesting in this set of maps where in the lower left-hand corner, investor-owned utilities, we don't have any because of our statute. So Nebraska is the only state with that statute, but we're not the only state with public utilities. Public utilities exist in all states in some form, but we're the only state that is 100%. So that's where we're a little different in that way, is that we have 100% public utilities. Now, these rate schedules, I need to update this slide past 2020, but it's not changed a lot. The idea is just the percentages, but there is 50,000 different rate schedules that are approved in the United States of America. So, to say that I'm charged for energy the same as someone else, there's lots and lots of different rate schedules. There's maybe 1,000 in Nebraska alone or more. There's 50,000 nationwide rate schedules. So when we look at that, how many of those rate schedules have demand as a line item in their rate schedule? Well, a lot of industrial customers and a lot of commercial customers have demand rates. As I said, those larger operations. But the residential, it's only 2%. But we're seeing an increase. And that's what I'm trying to kind of bring out here, is that we're seeing an increase in demand rates happen, and we need to react to that and maybe change some of our management that will help us save dollars. Just a little background, so we use the terminology right. When I'm talking about electricity, I'm going to say electrical energy is the total amount of work being done. So like the total amount at the end of the month, those units are kilowatt hours. Power is the rate, the instantaneous rate, how fast that energy was used or generated. And we usually measure these things in kW or kilowatts. Sometimes, because maybe I'm going to say it, we're silly Americans, we will actually convert kilowatts to horsepower to put it in a bill or something. I don't know why we do that, but we do. So kilowatts or horsepower are units of power. And so when we're charged at the end of the month, if the charge is per kilowatt hour, we're being charged for energy. If the charge is per kW, we're charged for power, that peak amount. So those terms are important. Let's review those really quick with some graphs. If I look at the amount of power on the y-axis and the amount of time on the x-axis, and I can see how electricity was used for this particular customer during this time period. And if I'm thinking about energy, I'm thinking about the total amount used. I'm just adding up the area under the curve. And that's the end of the billing period, and that's how much energy was used. Demand is going to be that peak moment. And so in this case, the demand might be, we'll call it, 105 kW. That is the peak moment in time. And we can imagine that the utility has to have infrastructure that's able to provide that peak moment, even though the moment was short. They need to have the infrastructure to provide that peak so that everything works properly. And so that's where that demand charge comes in, is at that peak moment. So let's look at a rate schedule example. Here is my very simple rate schedule. This is a Nebraska rate schedule with some numbers rounded off, and I'm not telling who it is, but it doesn't matter. They have a customer charge of $30 per month. They have an energy charge in the summer of 9.5 cents per kilowatt hour, and in the winter, 7.25 cents per kilowatt hour for all use. Very simple rate schedule. If you have a rate schedule that is like this, really your only avenue of trying to garner savings and at the end of a billing period or at the end of a year is to use less energy, because you're simply charged per kilowatt hour, and that's it. It didn't matter when you used it. It didn't matter the peak. It didn't matter you turned everything on at the same time. You're only charged per kilowatt hour. Thus, your only recourse is energy efficiency. And that energy efficiency, or turning things off, and that's, there's good and bad to that. It's simple, but it doesn't allow for much opportunity in savings, is as many other opportunities as there is for other rate schedules. But, look at your appliances, look at your lighting, look at your fans, look at your heating and cooling, and try to make a plan with regard to energy efficiency over time. And it's not that you are going to fix everything all at once, but you're going to work through that over time. This is the most simple rate schedule. It is probably the most common in Nebraska, but it is quickly becoming less common. right? We are starting to adopt these new and diverse changes very quickly in Nebraska. Here's an example of one. This is my rate schedule number 2 example, and I call it the energy rate schedule, where we're charged for energy as the primary charge. In the left-hand side, we're seeing what I'm calling a seasonal rate schedule, which is very similar to the rate schedule I just showed you. But I used the one on the left to show you the difference between it and the one on the right. The one on the right is a time of use rate. This rate is an available rate in the state of Nebraska for some customers. Currently, I think it's an opt-in for those customers to this rate schedule if they want it, but it is time of use, basically daily time of use. And you can see that those customers are charged 20 cents a kilowatt hour between 3 and 7 p.m. in the afternoon in the summertime. And they're charged 15 cents in the afternoon in the wintertime, and they're charged 15 cents in the morning in the wintertime. And so we can start to see that rate schedule is quite a bit different than this seasonal rate schedule, and how we react to it can really change things. Now, when I first saw this time use rate schedule, I thought that's kind of scary. 20 cents a kilowatt hour. Oh my goodness, it's expensive to use electricity. So I did some modeling, and I modeled the same house on an hourly basis with the seasonal rate schedule and with the time of use rate schedule. And this is what I came up with. I actually did 2 houses, a smaller house and a larger house. And what I came up with was that the annual cost of electricity for the different rate schedules is essentially identical between the 2 rate schedules with the same 2 houses. So it was about $789, $788 for the small house, and then about $1,300 for the large house. A little bit different, but not a lot different. And I think that there's something important here that we can garner from this. One is that we probably shouldn't be real scared of a time of use rate. If we don't change our behavior, a well-designed time of use rate doesn't penalize us too badly for that. But what it does do, if we had a time of use rate, is allows us an opportunity to move things off of that time. And so you can imagine our opportunities aren't just saving kilowatt hours. I had that on the last one. You just had to save kilowatt hours. You had to use less energy. Now we could use quite a bit of energy, but if we can move it off of these times. And so you can imagine maybe I used to start chores at 5 o'clock and turn a bunch of things on, or 6 o'clock. Maybe I could just delay that a little bit and load shift it so that I'm paying 8.7 cents for that electricity versus 20 cents. Maybe I could program some timers that turn things off or down as I move across these different time frames. And so in that case, I may not save any electricity, kilowatt hours, but I'm saving dollars because I'm paying less for the kilowatt hours that I'm buying. So this is where load shifting can be important. This is where a programmable thermostat is always important, but a programmable thermostat is really exciting in this type of a rate schedule, because now I can use it to really save quite a few dollars. Maybe really getting something cooled down or warmed up ahead when I'm paying 6.7 cents, and then I kind of float across that 15, 16 cent time without my electric furnace running or something like that. Just some examples of what I'm thinking about, where you're load shifting, trying to get these savings. So as your utility picks up these time of use rates, I want you to consider them, and don't be too scared of them, because they could be some good opportunity for you. Let's talk about demand a little bit. Again, this is our image of demand, which we're thinking about that peak time. Usually demand is measured in a time interval of 15 or 30 minutes. And so it's not an instantaneous peak. So some motors and things have very high turn on. You turn them on and they draw a whole bunch of power for a very short amount of time, maybe a couple of milliseconds. But this 15-minute rolling average is what they're usually measuring that on. So that kind of gets rid of that. But the challenge with demand is that it's harder to find out exactly when was that demand set and what was running when that demand was set, because I'm usually not monitoring my systems in that level of detail. So here's my demand rate schedule, number one. Monthly charge, $20. Demand charge, $10 per kW per month. Minimum billing demand, 20 kW. So if you use less than 20, they're charging you for 20 in this particular rate schedule. And then the energy usage is between 7 cents in the summer, and for the first 5,000 kilowatt hours, and a little less as you use more, and 6 and 4 in the winter. So in this case, and for this one, we'll look here in the lower left-hand corner, lower right-hand corner, excuse me, where I just ran an example month for this rate schedule. I said, what if I had a peak demand of 100 kW and I used 10,000 kilowatt hours electricity energy that month? My bill would be $1,000 for my demand and $600 for my energy. I am spending more because of that peak than I am actually buying kilowatt hours of energy. So it's very possible that I actually could garner greater savings by reducing my demand, by trying to find out when that peak was set and reduce it, than I could by actually saving kilowatt hours. Saving kilowatt hours is always good, but in this case, it may be secondary to trying to reduce that demand. So how do I reduce that demand? I need to discover when that demand was set, and I need to start looking at what was running at that moment in time, and can I change that? Maybe I can improve my systems to, or maybe I can replace some old equipment that doesn't have that peak, or maybe I just load shift again, taking something off of that time so that it's not adding up. I can always use less energy. I have some demand, I think I have a demand slide coming up again, but to go in more detail, but I wanted to get into another version of demand. This is a way rate schedules are written. I've not run into this in other places than Nebraska, but it probably exists in other places. So this is a different version of a demand rate schedule. So they had a customer charge that was different based on single phase or three phase. They have, I'm going to call it, say they have a demand charge, but it isn't spelled out as demand. It's down here in energy. So let's just look at summer here. They're charging 12 cents per kilowatt hour for the first 200 kilowatt hours per kW of billing demand, and then 4 cents for additional kilowatt hours. And then winter is pretty similar. So what does that mean? How does that work? So I did a version of it. We're back into the lower right-hand corner here. And in this case, I have a peak measured demand, an estimated peak measured demand of 35 kW. I use 10,000 kilowatt hours. So I'm going to pay 12 cents for the first 200 kilowatt hours times 35 for the first 7,000 kilowatt hours. So they're basically saying, if I have lower demand, I would actually pay that higher rate of 12 cents for less kilowatt hours. And thus, that's the second half of my month when I'm using kilowatt hours above that value, or I'm paying less. So in this case, the customer bill with this value is 960. Then I just ran an example and said, what if I got the billing demand down to 30 kW, dropped it by 5 kW, pretty good drop, but possible in some scenarios. I would pay $880 a month in that scenario, and I'd save, that $80 in that particular scenario by reducing my billing demand. And so it's interesting. It's weird to think about that we're charging per kilowatt hour with a demand rate, but that's how many utilities are doing it in Nebraska, particularly for irrigation systems, but I've seen it a few other places as well. So just be aware that that's what it means. Multiply the 200 or whatever value that is, multiply that by your billing demand, and that's how many kilowatt hours you're going to pay you the higher rate of 12 cents. And so the less time you can pay that, the quicker you can get into that 4-cent rate, you drop that price quite a bit. So here's an example from a dairy. I work with another educator in Ohio, and he collected some data off of a dairy, and I've been using some of that as well as him for some educational purposes. And so this is 5-minute increment data from a dairy across the whole year, but we're looking at it on a particular day. And why did we pick this day? Because this was the day that our 15-minute peak was set, and this is the day we're charged that set our demand rate for that year. So when we look at that, we're going to zoom into that rate and say, what in the heck was happening at that moment in time? And the fans were running, the vacuum pump was running, the cooler was running, the milk cooler, the water in the feeder was running, and the manure pump was running. And that set our peak. And so what this particular operation discovered was that this peak was pretty significant. And you can see that this manure pump is 25 kW, pretty significant demand right there. And what they were discovered was that manure pump, the person going into milk would in the morning would just flip the switch to turn on the manure pump because it had to run for an hour and a half a day. It didn't matter when it ran, it just had to run an hour and a half a day. And so what they were able to do was then just decide, we are going to move this manure pump turn on with a timer to the middle of the night, and had very, very significant savings because of that. Now, this is a great example of where it works perfect. Your examples may not be as perfect. The other thing, your level of data, at least initially, is not going to be this good. So there could be some trial and error in this, but discovering when that was, mine was set at 8:15 a.m. on July 15th, and thinking about what was happening at 8:15 a.m. at my operation during that time. And is there anything that is not critical that doesn't have to happen at that time? Can we do some load shifting to try to reduce that? And that's, again, starting to make a list of all of the loads that you have. This pump was on, this pump was on, these lights were on, these fans were on. Some of those we are not going to turn off. We are not going to turn off those fans. We are not going to turn off the coolers or the vacuum pump. Maybe the feed and water could change a little bit, but the manure pump in this case could move. So there's these loads that can change and loads that can't. Be cognizant of that. And that's where sometimes it's going to be a trickier way to try to save in that. Let's change gears a little bit. My last topic is power factor. Power factor is a little bit more complex, but is maybe one of the easiest ways to save or prevent being charged, but understanding it's a little complicated. Power factor is a measure of how effectively equipment converts electrical power into useful power output. So power factor can be low in inductive loads like electric motors, transformer, high intensity discharge lighting. Electric motors are the one we run what we run into in farms the most. Electric motors can cause low power factor, which then some of those costs are now being put on to the farmer because we're measuring them better. One of the better explanations of power factor that I like is to think about that the working power in the electricity that we're being provided does useful work and is measured in kW, and we're charged for it in kW. but the utility has to provide us both working power and non-working power. Non-working power in this case goes into the stator of the generator to keep everything energized. It doesn't do any work, and we're not typically being charged for it. We're being charged for kW, not kVAR. Kilovolts reactive is what kVAR is in this case. So the utility had to provide us total power, and yet we're only being charged for working power. And so as our power factor gets worse, the ratio between working power and non-working power, and thus they're providing us quite a bit more, and then they're not getting anything back for it. So they're having to adjust for power factor on their side and pay for power factor on their side, but the customers aren't paying for it, or all customers are paying for it, but the customers causing that problem are not. Now the customers are now being charged for that power factor problem. So just a way to think about it is that the utility has to provide both active power and reactive power. Another word for that is working power and non-working power. Has to provide both to us, yet we're only being charged for the active or working power. One of my favorite kind of ways to think about power factor is to think about a trolley on a railroad track being pulled by a horse, but the horse can't walk on the railroad track. It has to walk beside. So to provide working power that moves that trolley forward, that horse has to pull in two different angles and actually has to work harder to get that trolley to move. And so it has to provide both working power and non-working power so that that trolley will move. And so I have to have a bigger horse. I have to feed the horse more. And yet the work being done is what's being measured in kW. Well, we got to pay for the bigger horse and for the bigger feed bill. So let's look at a rate schedule for power factor as we get closer to done here. $20 a month monthly charge, $10 per kilowatt demand charge. Again, minimum 20 kW for demand with a power factor adjustment. If the ratio of working to non-working power is 0.9 or above, no problem. If it is below 0.9, we're going to adjust the demand by multiplying the billing demand by 0.9 and dividing by the recorded power factor, and thus get a new demand charge that is what we're going to pay for. So let's go back and figure out how that might work out. Back down to the lower right-hand corner. If our measured power factor is 0.8, I take my billing demand of 100 times 0.9, divide by 0.8, I get 112. Instead of being billed for 100 kW, I'm now going to be billed for 112.5. My power factor, low power factor, adjusted up my demand so that I pay 1,125 for demand and 600 for energy. That's generally how power factor charges appear and are calculated on your bill. What can we do to save on that? Power factor correction. The good news is this is one of the easiest costs to avoid with power factor correction devices. The second would be, again, reducing demand, trying to figure out how do we reduce the overall demand so that we can save and always use less energy. So when we add power factor correction devices, these are simply boxes of capacitors. Capacitors are like batteries that aren't chemical. They actually store electric charges. And what that capacitor does is actually can provide some of the reactive power to the system. Thus, when I have less reactive power or non-working power, I can actually reduce the total power, thus improving the power factor. And all I did was add a capacitor bank to the system. As long as that capacitor bank is functioning when the motor is functioning, I have a better power factor and can avoid some, and in many cases, all of those charges. Again, that's $112 for that billing period, gone. Don't have to pay it because um, because I had that power factor correction that just made my 0.8 to 0.9 or better. Okay. So if you have power factor on your bill, here's a couple of things I wanted to note. You want to add or maintain power factor correction capacitors to your large motors or to your panels that have lots of large motors on them. There's different types of capacitor banks. You can put big ones by the panel, or you can put littler ones on each motor. Different pros and cons to each of those. You want to add those. Some utilities on irrigation systems have required these for years, but not charged for power factor. Now we're adopting the power factor charges. So some people in Nebraska are going to discover they already have the power factor correction device there. All we have to do is make sure it's working. So then it is just maintain that system. Many irrigation customers pay annual or semi-annual bills. This is a little bit of an interesting situation for power factor because if the capacitors fail in mid-season, we may not know it, and thus we get this bill with a bad power factor, even though we corrected for it. So we want to be kind of watching for that and maybe challenging our utilities to, we proved that our power factor was good. We didn't have any way to identify that in mid-season. So how do we work with our utility to kind of remedy that situation? So monitoring those is going to be interesting because it's just a box. There's nothing that tells us it's on. And the power factor on our meter isn't in real time. It is the power factor at the peak, back at that demand peak time, which may have been set a month ago. So we don't have that real-time power factor. The utility might, and you could call them and ask for it, but we don't. Many customers aren't going to have that real-time power factor to see if that power factor correction is working. So just something to think about. Okay, I think I'm going to end here just so we can go to get the most questions possible. But I'm going to end with kind of a thought process, and that thought process is you need to get your rate schedule. You need to understand, are you charged primarily for energy, demand? Is power factor part of your electric bill? And once you do that, you can then begin to make a plan over time of how you're going to try to reduce your costs for electricity. The other thing I want to say is that it's just a strategy, but these rate schedule changes tend to creep up on us, and we tend to not see them till after the bills come. So I would really encourage you to read your utilities newsletter every time it comes out. And I'm not saying read every word, that's hard, I don't know. Read the headlines, make sure that you're not surprised by a rate schedule change that's coming. And you then communicate with your utility if you like or dislike those changes. But it is important to read that newsletter because that's where they're going to communicate with you. And I know we all don't do a good job with that. I know I don't. So I'll turn it over for questions. If anybody has any questions, please type them in now or go ahead and ask in other ways if you can. But I think we're typing them in. So.
Yeah, John, maybe while people are submitting questions, I'll just throw out there my experience working with facilities, rural facilities, whether it's a livestock building or a shop or a irrigation setup is I'm surprised to find how many different rate schedules are out there and how many people just assume that they're just paying for energy, and it will frequently come up that they're paying for power in some way.
Yeah, that demand, this demand thing is going to really creep up on us. I saw a rate schedule yesterday that is a change for 2024 that had $1.50 per kW demand charge at a residential rate schedule. And in that case, and it is what it is, they lowered the per kilowatt hour energy and added this demand charge. Well, that's, very potentially, $15 or $20 a month that is paid for in demand. That it's just a different way of charging. Again, I'm not arguing about philosophy. It's just that it is really be good to the customer understood how they were charged so that they could begin to reduce that.
So I'll mention a couple of triggers. One trigger that I've seen is somebody buys property and they want the land, and they get the buildings with the old buildings with the land, and the old buildings had some motors in them, and they never used the motors, but the utility knows that those motors are there, and so there's some rate schedule that says that they're charged based on the total kW or horsepower capacity of the site. And so even though they never run those motors, they're still being charged for them. And they might say to the utility, well, I never turn them on. And they say, well, you could. And so the solution is to disconnect those, have them taken off the public utility line.
Really good points, because in this case it's a version of kind of a minimum demand, but what the utility's trying to do is say, like, right, you could turn all those on and have this much demand. We need to have that much available to you, so we're going to base our charge based on that. While they're saying, well, I never use it, so don't charge me for it. They both have good points. And so the question is, it just came in, can you give any detailed advice on how to improve my center pivot irrigation energy charges? So in center pivot irrigation, most of the rate schedules are going to be based on interruptibility or load control. So you can sign up for a rate schedule that says you can't ever turn me off. You can sign up for a rate schedule that maybe says, well, the utility can turn my pivot off on Tuesdays and Thursdays. You can sign up for a rate schedule that says you can turn me off any day of the week, any time of day, and et cetera. And as you allow for more load control, more control from the utility of when that can run that pivot, you're going to get better and better prices. So very expensive if you never turn off, better if you don't. So that's one place, and you might understand that, but I was trying to explain to the whole group. So obviously, trying to justify which is the right one to try to save. This power factor can add as much as $500 to a individual center pivot per year in costs if you have poor power factor. And so it is going to be important to note, am I charged for power factor? Do I have power factor correction? Do I have the right power factor correction? Is it functioning? And so that's going to be a very quick savings, as much as $500 a year, with an investment that may not be too significant. Now, these power factor correction devices can be $200 to $500 themselves, but if you're saving up to $500 a year, that pays for itself pretty quickly. The other thing is, and this is a little harder, but I've seen a lot of electric irrigation systems that the motor was oversized and running inefficiently. And I can understand how that happens. The motor goes out, the company, you call them up, oh, I got this motor sitting on the shelf, we'll put a new one in, but it's oversized. And you got two problems when you oversize a a motor. One is it runs much more inefficiently in and of itself. The second is that power factor is best, highest, when the motor is running at full capacity or closer to full capacity. And if you're running it at partial capacity, your power factor is worse. And so you're kind of being double dipped by having inefficient, oversized motors. It's weird to say I have too much power, but I have a motor that's oversized. That's a problem in many irrigation systems. Rick, what do you have to say about that?
I was just going to chime in that I'm seeing the same problem in a lot of our facilities, and it's on all types of energy consuming equipment, but specifically to electricity. The solution has seemed to be variable speed, variable output motors and equipment. But the problem is that encourages people to go big, and they tend to go oversized and then run it at a lower speed, and they're actually being dinged because the power factor is poor at those low speeds, and if they go oversized, it's kind of a double whammy. They're oversized and then they're running at a poor efficiency.
Yeah, that's excellent. Another thing I thought of, I'm just trying to think through many of the ways you can save with the center pivot, but again, looking at that rate schedule and saying, what are my billing time periods? If I'm billed in this, for kind of the winter time period, the summer time period, and the fall time period, which is some of what I've seen, you may end up really causing yourself a problem by turning that pivot on before that time, that billing period change. Because if I turn that pivot on, let's say in March, just to, I don't know, water in some herbicide or test it, I am setting a peak and a power factor in that time frame that I'm going to have to pay for, and I might pay $25 a horsepower or something. I don't know what the numbers are in different places, or $10 a horsepower or whatever it is, but I'm paying for that. While if I didn't turn it on till the breakover in, I'll call it May, all of a sudden I turn it on in May and I only get charged that power factor once during that billing period. So you can cause yourself some really high expense by turning things on and running them. You thought it was convenient, but it cost you a lot. So just double checking how that rate schedule charges and what are those different billing periods can really help as well to kind of just avoid these silly charges that you didn't expect. And I only call them silly because, you only ran it for a little bit and you thought you were doing something good, but it ended up not being as good, and it could have been avoidable. So, well, very good. Thank you all for joining today. If you have any last questions, we'll get to them, but otherwise we'll turn it back to Ryan.
Thank you, John. Thank you, Rick, for both being here and putting this together today. Great presentation, and really appreciate the opportunity to work with you again here through the Center for Ag Profitability's webinar series. And for people on right now who would like to revisit this, you can see the link I put in the chat. This recording should be up on our center's webinar page in the archive section later today if you check out cap.unl.edu/webinars. We'll be back on Monday with our agricultural land management quarterly webinar looking at cash rents and setting leases for 2024. That's Monday at noon. Again, you can register on our website at cap.unl.edu. And I want to thank John and Rick again for their time and a great presentation, and thank you for attending. As you close out today, you'll be presented with a very short survey. If you could just provide your quick feedback on today's webinar, and we would especially love to hear any ideas you might have for future webinars you would like to see. Have a great afternoon.